So we're going to move on to thermal efficiency and energy reuse, which is really common now in Formula One. I'd like you to cover a few things about how that can be applied to other industries. Can you share an example of how, like, waste heat, like from a brakes of a car or refrigeration systems, is reused in another part of the system, and kind of what impact that has?
Absolutely. I think to start with the Formula One application, the general concept around the modern power units within Formula One and also within Formula E and so forth and other formulae like that is very much about energy recovery, as you touched upon. The ability to understand that energy is never lost, is never created, it's always just converted. So with that in mind, you can understand there are certain areas where energy is purely converted from one source to another, and if you don't understand the source that you're converting to and the potential use for that energy, then you run the risk of creating an inefficient system. So within Formula One, as we said, there is energy recovery regarding the braking systems and putting energy through the engine back into the battery. But of course, they do lose energy from braking, because every time you apply the brake pedal, all you're actually doing is converting kinetic energy into heat energy, and that is a huge loss of energy. When you consider the mass and velocity of a vehicle. So that mentality really allows you to focus on the approach of harvesting and scavenging every single piece of energy you can get. So other applications that can use this are things like refrigeration units, where a refrigerator's pure purpose is to create cold air to keep your food cool effectively. However, the way it does that is by energy transfer, and that in itself creates some heat. If you fill the back of your refrigerator, it's hot, obviously. Now, whilst you probably benefit from this, you don't realise you're benefiting from it. In the winter, that heat from the refrigerator is obviously heating your house generally. So whilst you may not measure it because it's quite a small number, you could potentially compared to having the fridge off, you could actually have the fridge on and have the thermostat working slightly less hard and have your boiler working less hard in your house, because you're benefiting from that heat that you're producing from the refrigerator, the back of the refrigerator in this case. However, the key is that's an example of understanding that the heat and the energy is there and you can use it if you want to. So the real key is to understand where that heat can be used. The worst thing you can do is exhaust hot air outside to the outside atmosphere and then also be creating heat and burning fuel to create heat inside. You may as well keep that heat inside. So simple systems like ducting heat from a refrigeration unit into a building when you actually want to have a heated building are clear ways you can save energy. And again, it's a minimal effect initially, but actually cumulatively they add up to quite a large and significant effect that can benefit the user.
How many businesses do you think do this? Obviously there are businesses with large units that expel heat, including refrigeration, at scale. How many businesses actually utilize that heat?
It's one of those examples where I think businesses will typically utilize that heat and that energy and take the concept to the first level. And I always refer to like peeling layers of an onion. The first level everybody does. So for example, in automotive, MGUKs or hybrid systems where you don't apply the brake pedal, but you put energy through a motor and put it into a battery that you can then use to deploy later for acceleration. A lot of people are doing that, and it's a very, very obvious way to save some energy. However, a typical drive cycle, you can't always do that. And with that in mind, you end up having to use the friction brakes and you still have that wasted heat. So that's what I'd call the second or maybe the third layer of the onion, where you're actually in a position now where I'm doing the first thing, we all know that. And I think to answer your question directly, a lot of places I think are doing the first level. They are starting to recognize, for example, if I'm running the air conditioning, I'm going to close the windows to make use of that. But the second version is other heat devices, other energy devices, to use those and to make best use of that energy. So I think to answer your question, a lot of people are probably doing it already, but only to the first level, only to a very introductory level, and therefore the benefit is reduced. I guess it's capturing the low-hanging fruit, where you take that first piece, which is great, and then you pat yourself on the back. But in reality, you want to go to the next level and the next level down, and that's when you can really start making a difference.
So yeah, I'm assuming you can switch it. So in the winter months, you can use it internally, and in the summer months, you can vent it outside.
Absolutely, and if you take the example of a refrigerator, ideally when it's ideally, when it's cold outside, you want to just open the door and allow your food to be cooled by the external atmosphere, and then you essentially have the refrigerator off. And in the same way, in the winter, in the summer, you may want that fridge on, obviously, and then you need to get rid of the extra heat, otherwise you're heating up your house, and then also air conditioning as well. So it's understanding the most efficient source of energy for the task you're trying to do.
So how do you design these thermal systems? Can they be? Do they have to go on a new design in a new plant, for example, or can they be retrofitted?
I think it's a case of the adaptation, effectively. The key thing you need to do is look at the whole system at a very high level, and you need to understand all of the inputs, and you need to understand and view that system with a particular lens, let's say, so that you are looking at, there's heat generated there, there's cooling requirement there, and you can actually piece that whole system together to understand how to make best use of the energy and the energy transfer you've got going on in the system. And then I think the adaptation is probably an easy way to get some aspects effectively, but then there are some more complex characteristics, let's say, that you would need to have fresh designs for effectively. And then it becomes a cost benefit ratio to understand how much it's worth spending to do this versus the saving you may potentially get. But obviously, when you're doing that analysis, you need to look at what other opportunities that then opens. So, for example, heat pumps in a house, not using gas but using electricity for heating, whilst that has its own benefit in the first instance, when combined with energy storage systems and solar panels, it actually then produces a solution you didn't have available to you before in different areas of the house.
So away from, let's take refrigeration away from now. What lessons from F1 thermal management have been useful in other sectors like rail or logistics?
There's an obvious example where you have a train or perhaps an underground system, for example, which is operating with electric motors these days, and of course the concept of regenerating energy through the motors into the battery or back into the grid during braking occurrences is an obvious application, which is very easy to apply when you have electric motors on your drivetrain effectively. However, it's actually interesting to understand that many years ago, well before my time, the railway system there operated with the same sort of system with energy conversion, whereby the rail platforms were actually raised slightly. So a train running along a straight bit of rail track, as it approached a station, it would be going uphill, and that would therefore be converting that kinetic energy into potential energy. Then it stops at the train station, loads up its passengers, and as it sets off, it then runs downhill slightly, converting that potential energy back into kinetic energy. So I think that's a system that's been in place for, like I say, many decades, possibly even hundreds of years. But it's worth understanding the very simple concepts and how you don't need to have a very complicated and expensive power electronic switching system. You can also use natural energy and energy movement and energy transfer around you, and obvious ones are with aqueducts and with running through electrical generators. When you move the water level in peak times from a reservoir, you use that potential energy to create electrical energy when you need it, and then at more efficient times you pump that water back up. So you're using the potential energy of the water as energy store. So I think considering these adjacent technologies effectively and these adjacent engineering principles is quite interesting, and it's something that is also quite interesting where graduates and kind of new inexperienced engineers, these are areas where they bring a fresh approach to this sort of challenge, whereas people have been converting kinetic energy through motors for many years. There is some efficiency still related to that, whereas a conversion to potential energy or, as you say, water storage in these sort of areas can be seems too simple, but actually a lot of this property and this process benefits from a simple approach effectively.
So other than we've covered costs and return on investment, what other key factors are there to consider when deciding if a system is suitable for heat recovery or reusage?
I think, as you've said, the cost and the cost and return on investment are critical, and in truth, many times that is the most applicable source. The world tends to run on the finances. However, I think what I would say is the key is to expand upon the first level, and whereas a very basic cost model may provide a return on investment. I think the key to this is actually understanding the bigger system and the opportunities that may open up effectively. So if I make this conversion, it's a marginal business case or a cost model as to whether or not it's worth doing. But however, once I've made this change, the next change becomes a much more beneficial cost model because you're already working, let's say, in the right currency as far as energy is concerned. And this is a point relating to, as I say, heat pumps. Whereas they're more efficient converting power into heat, more efficient than using the electricity rather than the gas effectively. But by the fact that you're then dealing in electricity, it does allow you to benefit from battery storage, vehicle to grid in road cars, solar power, wind power, the list goes on. If you start to use your currency of energy being in electricity, then you open up a far greater array and a catalogue effectively of benefits that you can obtain.
I suppose it also enhances reduces the carbon footprint of businesses, doesn't it? Because everybody in manufacturing's got these energy targets now. Is that a factor too, that it's not necessarily cost or
exactly
return on investment? Yeah,
absolutely, and that's part of the point about having chargers at the workplace, for example. You can make sure that when your staff come to work and they plug in their cars, if they're able to power the factory from their cars effectively for the first part of the day when the usage is higher, and then you pass the energy back and they charge their cars back up to capacity to drive home in the evening, that's a fantastic model. And that's where, however big you think the system is, you can always take a step back and see the bigger system. And this is an example where, talking about energy usage, people are concerned about can the infrastructure and can our energy production provide for all these electric cars, and they think the electric cars are a problem because of that, with everybody coming in and plugging in their car at 6 o'clock in the evening. But actually, with vehicle to grid and with that energy transfer into the home and onto the grid from a charged vehicle during peak times, you actually allow electric cars to become the solution, and you can really flatten the energy usage and the energy consumption for the whole country effectively.